Good afternoon, everyone, and welcome to the third brown bag in the Department of Geography and Geology's 2021-22 series of seminars. This afternoon, we're going to be exploring with Ms. Tiffany Wallace from the ICENS Center at UE, the topic of greenhouse gas emissions, and just a little bit of background to her talk. The long-term temperature goal of the Paris Climate Agreement aims to reduce global warming to well below 2 degrees Celsius above pre-industrial levels by the end of this century. The nationally determined contributions, NDCs, which target sectoral emissions reductions, is at the heart of the Paris Agreement. However, the recent ensemble, which is basically a model of the NDCs, indicates that the average global temperature is on a trajectory to reach 3.4 degrees Celsius and will further imperil sustainable development. The land sector is the only sector that provides a feasible and cost-effective option to significantly reduce carbon dioxide emissions, leading to carbon neutrality. To achieve this, accurate carbon accounting is imperative. The talk today provides a preliminary account of carbon emissions and removals from the forestry and other land use sector using remotely sensed data. And our presenter is Ms. Tiffany Wallace, as I've mentioned, and she's scientific officer and environmental research scientist, and she has a keen interest in climate change resilience in small island developing states. She's a member of the Food and Land Use Development Team of the Caribbean Cooperative MRV Hub, which is responsible for the measurement, reporting, and verification of land-based greenhouse gas emissions across 12 CARICOM countries. She has worked as a research assistant for the Agrobiodiversity, Indigenous Knowledge, and Protected Area Management in the Rio Grande Valley, Jamaica, and KwaZulu-Natal, South Africa project, as well as the assessment and economic valuation of coastal protection services provided by mangroves in Jamaica project. Her areas of expertise include remote sensing, collection of environmental samples, and determining carbon stocks for above and below ground living biomass and the soil carbon pool. She received her BSc in chemistry from the University of the West Indies, Mona. So she's homegrown UWI Mona talent, and she has added to that by acquiring a certificate of proficiency from the IPCC in forestry and other land use inventorying from the Greenhouse Gas Management Institute. It is my pleasure to welcome Ms. Wallace to present today's seminar.
Good afternoon, everyone, and thank you for joining me today. I'm just trying to share my screen here. Are you able to see my screen?
Yes, you're in full screen mode now.
All right, so good afternoon again, and thank you for joining this presentation. Today, I will be presenting on measuring, reporting, and verification of land-based greenhouse gas emission using remotely sensed data. Before I go any further, I would like to acknowledge the other persons of the FALU development team that played an essential role in the preparation of this work, and they are Alicia Edwards, a GIS expert from the Forestry Department, and Dr. Adrian Spence, the Senior Research Scientist at ICENS. So a bit of a background about the Caribbean Cooperative MRV Hub. It is a project of the Greenhouse Gas Management Institute and therefore a part of the Climate Initiative. It was implemented with the goal of building technical capacity for local experts to establish MRV systems and to develop accurate greenhouse gas inventories, as well as to monitor the effectiveness of mitigation actions and policies, as well as to track the progress of NDCs. It comprises, among the 6 sectors, it comprises of the 12 member countries. However, for the FALU sector, I believe there are only 4 countries that are involved, which is Jamaica, Guyana, Belize, and Trinidad and Tobago. Our team lead is Mr. Anup Joshi, and he is a senior fellow at the Greenhouse Gas Management Institute. And if you would like to find out further information about the work that is being done by this hub, you can visit the website that is displayed on screen. So I do believe that this presentation is coming at an ideal time, especially with the conversations that we have been having around climate change. As you know, the COP26 is occurring right now. And so I think this is an opportune time for us to be having this conversation. But just to reiterate the main points, the long-term goal of the Paris Agreement is to reduce global warming to well below 2 degrees through the removal of atmospheric CO2 by cuts in emission and the improvement of our natural sink. And at the heart of the Paris Agreement is the national determined contributions, which are the government's commitment to reducing emission. If we look to the figure on the left, I hope you can see it clearly. And it shows some general pathways and scenarios that can lead to a 1.5 degrees Celsius pathway or a 2 degrees Celsius pathway by the end of the century. But what is important to note here is that based on the current ensemble of NDCs, both the unconditional scenarios and the conditional scenarios, we are projected to land at about 3.4 degrees Celsius by the end of the century. And what that is saying is that despite our best efforts to date, we still have a gap of, we need to cut emissions by about 32 gigatons of carbon per year if we were to achieve these goals. Now, achieving these goals, as the Prime Minister of Barbados would have said earlier in her talk, it becomes, for us as members of the small island developing states, more than just achieving our sustainable development goals. It now becomes a matter of life, protecting lives and livelihood. And so you may ask, why would we focus on the forest and land use sector when the sectors that contribute most significantly to CO2 emissions globally, well, usually is the energy and the industry sector. And that is because the FALU sector provides the only feasible option to enhance the removal of CO2 from the atmosphere at scales that can lead to carbon neutrality. While there are other options, such as the capturing of CO2 from industries and sequestration in geological formation, those options are technology dependent and very costly. It also requires extensive monitoring, as those CO2 sequestered or stored in the rocks can still escape and re-enter the atmosphere. As such, well-managed land plays a vital role in mitigation across all sectors, including the energy and the industry sector. And that is why, well, that's why I have chosen to focus on this area. So just to set some background, to lay some groundwork before getting into the body of the presentation, I'd like to just introduce you to the Google Earth coding environment, and that is what we have used to acquire our remotely sensed data. The environment composes of 4 main components, which is the, I'm not sure if you're seeing the pointer on the screen, okay, which composes of the script manager, where you can view sample codes. You can save the codes that you have written. There is a docs tab that allows you to research commands to assist you with writing your code. And there's an asset tab that allows you to save assets such as training data, validation data sets, which we'll discuss further in the presentation. The second panel or component is the code editor, which is where we would write and run our codes. Then we have panel C, which has the console output, the task manager, and the inspector tab. So the console allows us to view processes that has been executed from our coding. The task tab, for some processes are a bit more time consuming than others, and the task manager allows us to view the amount of time that is left for the task to be completed, and the inspector tab allows us to actually inspect different values that has been inputted to the map, which brings us to the 4th panel, which is the map viewer. And it basically gives us like a visual representation of what we have written in our codes in this section by a simple command, add map layer. So if you're familiar with any type of GIS software, I think it's similar for most. The next overview that I would like to provide you with is basically a workflow of what we do in this Google code environment, and that is we import composite image, which is a collection of image from satellite data, and then we collect training data from this image after it has been manipulated, and we'll go through each step in detail throughout the presentation. Once we have collected our training data, we are able to develop a model, or what we call a classifier, to build land use classified maps, which is outputted or visualized in the map viewer environment. These maps are then validated, and we assess the accuracy of the maps. And based on the accuracy, we would be aware of whether we can continue with our process, or if we would need to go back and include more training data or improve the training data, which we'll discuss again further, and repeat this process, or if we can go ahead with our inventorying process. All right, so we're going to go through each step of the workflow individually. So the first step is that we import a collection of image from a satellite program. For our work, we have been working with the Landsat program, and this collection of images filter and manipulated to produce one median image that kind of gives us the average of what the area is like for that period. So we do this by, first we filter by cloud cover. So we'd say to the program, okay, I want a picture of Jamaica that doesn't have more than 20% clouds in the atmosphere, because we can't classify areas that are under clouds or in cloud shadow easily. Well, we can't do it. And we also, one of the way that we help to do that filter is that we filter by date range. We usually try to select dry months, so those would be the time when we have the least amount of clouds, or we might extend the date range for the entire inventory year based on the quality of the data after we inspect it. And then we display this image in the map viewer section. So here's an example of the true image of Jamaica for 2020, and it was collected from the Landsat 8 Tier 1 surface reflectance collection of images. Once we have our true image and we looked at it, and we've inspected and it looks fine. You have a few clouds here, but I mean, that's the best option based on our checks. Then we would begin collecting training data. So training data represent points or polygons that accurately represent stable land cover and land use on the ground. So we apply the training data to the image to collect information on the band. So within that polygon that we have selected, then the pixel would have a range of values for each band within that pixel. And we would assign those bands to a particular class. So for example, I know that in this area, the Blue Mountain area, that it has been forest and we're expected to stay forest for a very long time because it's a protected forest area. And so I can collect polygons, training data from this area. I would assign it to a class forest, and I would give it a numerical value of 1. So this training data was collected by visual determination. There are other land use types that are a bit more difficult to see just by inspecting the map. And for example, like other land use, which represent land that has little to no organic carbon matter in the land or on the land, such as bauxitic soil or rocky soils. And for those situations, we would overlay existing map covers, and these were provided by the Forestry Department, onto the map to be able to identify those areas that form other land use categories. And so this was done. So we collected our training data using 2 approaches. We used visual determination and by using existing land cover maps from the Forestry Department. So once we have our training data set, we use this training data, the information from the training data set, to basically program a inbuilt algorithm in Google Earth to develop a model, or what we call a classifier. The classifier is then used to predict the land cover of the entire image based on the sample of image features that we have assigned to each class. Because based on the scope of this study, we have used a class that align with the IPCC land classification system, and we represent them by unique colors. And these class would be cropland, with forest land, cropland, grassland, wetland, settlement, and other land. So with our trained classifier that we have prepared from our 2020 image, and usually you use the most recent image because you're able to say with some level of certainty that that is what is on ground by going out and doing our ground truthing. We are able to classify all the other maps, images for the previous inventory years. So this is an example of our classified map for 2020. We see where each class, land use class, is represented by a different color, as said before. So we have the forest land in green, cropland in yellow, settlement land in red, and so on and so forth. And we display this image in our map viewer environment by just using the simple command add map layer. So some more examples of the classified maps we have from 2000 going all the way up to 2020, which we just saw before. You'd notice that some of the maps have a bit more clouds than others. That has to do with basically the collection of satellite image that we have used and just the general environment at the time that the satellite images were taken. And we'll discuss that later on, how the clouds and the cloud shadow affect the classification. So once we have our maps, they won't mean anything unless what we're seeing in the classified image reflects what is on the ground. And so to validate the land cover types of the classified map, we use high resolution satellite data to do digital verification. So here we again collect points or polygon from each class from the Google Earth image data set, but now these are termed validation data. We try to collect the validation data from the same location, and we try to collect the same attribute, but they must not overlap with the polygons that we had created before for the training data set. And the validation set is used to evaluate how well the model performed. And from this, we can get in our console a number for the overall accuracy, the user accuracy, and the producer accuracy. Usually you want an accuracy value of about 85% or higher. Under this, then you might need to go back to your training data, collect more accurate training data, or probably delete some that overlaps with some land use types. And you'd have to go over the step until you have an accuracy of about 85% or more. That means that at any point in time, if you're supposed to pick a point from our classified map, then there's an 85% chance that it would reflect what is on ground. So we did our classification. The maps have been validated, 85% accuracy. And so now we can move on into seeing which areas between our inventory time period have transitioned from one land use type to the other. And we do this by subtracting two classification maps from the two consecutive inventory period. And usually in land use assessment, we use an inventory period of 5 years. To identify so this shows a transition map. It's the land class map of 2005, of 2010, sorry, subtracted from 2005. The areas in white represent land use type that has not converted over the 5-year period, and the areas in red would represent the areas that has been converted from one land use type to the other. Just to note, the reason why this looks as red as it does is because of the scale that we're viewing it in. However, if you were to be looking at this in the Google Earth environment and you were to zoom in, then you see that these are highly disaggregated and very pixelated, so you can see each area differently. It doesn't look so clustered as it does now. All right, so on this map, we can see, okay, some areas here have converted from one land use type to the other, but you can't see which ones. To identify the unique transitions, then you'd have to view that in the console. And as said before, each class would have been given some numerical value. So for the forest class, we would have assigned a numerical value of say 1, and the croplands, we would have assigned a numerical value of 2. We'll have 2 and 3 here. So let's say we assign forest land to class 2 and cropland to class 3. Then we would have just multiplied, simple mathematical manipulation will multiply class 2, the 2, by 100 for a map that was classified in 2005. And then we would have added to the second map, and so we get a value of 203 in the console that would indicate that an area that was previously a forest land in 2005 has been converted into cropland when we went to do our inventory in 2010. This also gives us the number of pixels that has been converted, and we can also use some simple mathematical conversions to get the number of pixels to the hectare of land that has been converted that we will be using for activity data. So the activity data, once we have our activity data, then we can estimate emissions or removals by these basic fundamental emission factor, which is activity data by emission factor. So activity data is just basically the activity that relates to some source of emission. For us, it would be land. If we were looking at like agriculture, then it might be the number of animals on a farm that contribute to methane emission, for example, or for the energy sector, it would be the amount of fuel consumption that contributes to emission. And then the emission factor is the quantity of gas, whether it is that you're looking at methane or carbon dioxide, that is being emitted by this quantity of activity. And so just by multiplying the two, then you would get an emission or removal estimate, which is what we have done in our Excel spreadsheet. So this is the fun part, well, for me. We have the values here that I would have spoken about before, the numerical codes that talks about transition. So 1 was for the forest class, 01 means forest class remaining forest class. We would have received the activity data in the console, which we can copy and paste, or we can write a code to import it as a CSV file. And I have placed what these codes mean in words for ease of understanding. So we have forest land remaining forest land, and we have this hectare of land that falls into that category. So we are able to calculate the emission factor, and we get this. We have used the IPCC default values for the calculation of our emission factors, which is basically the carbon stock. And the carbon stock is as I said before, a default value based on the climate, the region, and the land use type at time 1. And again, for that same parcel of land, the climate, the region, and the land use type, you'd expect this amount of carbon to be present at time 2. And by subtracting the carbon stock at time 2 from the carbon stock at time 1, we get our emission factor. And we do this for all the possible conversions or non-conversions of land. And what is important to note here is that when a forest land remains forest land, then we have a negative emission factor. Also, when any type of land is converted to forest land, we also have negative emission. Once a forest land is being converted to any other type of land, then we'd have positive emissions. Negative emission factors and negative carbon emission means that the carbon is being removed from the atmosphere. And while the positive emission factor and positive emissions would mean that the carbon dioxide is being released to the atmosphere, which is what we don't want. We want to see net negative emissions, meaning that the forest lands are removing more carbon dioxide than is being released. So just the options there, all the possibilities, and this can also, the information that was shown previously can also be displayed by a land conversion matrix. Here we have the land conversion matrix of 2005 to 2010. We see all the options here, forest land, cropland, so on and so forth. In the row and on the first column, the values in the diagonal represent the hectare of land that has remained unconverted. As we go across, we see, for example, how much hectares of land is going from these other land use type into our forest to give us a final area at the end of our inventory period, which would be 2010. And as we go down the columns, we see how much area of forest or forest category is being lost to the other land use type to give us this value here. which is just a simplified view of what I would have spoken about previously in the first Excel sheet. What is important to note here is that these values should be equal to each other, and they should be equal to the total land area of the country that we are doing our inventory for. As you can see here, there's a bit of a gap between what is the total land area for Jamaica and the value that we have here. And typically, this is due to, as said before, the clouds and the cloud cover, the cloud shadow, sorry. And what we had done is, for the clouds that we could not avoid, we wrote a function to basically mask the clouds so they appear invisible. We could have found a solution to this problem by just looking at areas that the clouds are and doing an assessment of whether they are still forest, remaining forest. It's usually in the Portland parishes where you have those high level of rainfall, so you can't really escape the clouds. So we could have just looked there and say, oh, we know this is a Blue Mountain area and it is forest that has remained forest, and we could have put the difference here in this category. But as I said, this is preliminary work, so maybe we will do that in the future to refine our values. But this isn't too bad. Okay, so once we have our activity data, which we got from our remotely sensed data, and we have the emission factors, and we sum all the categories that was seen in the Excel sheet, then we can tell the total carbon emission over a 5-year period. And by dividing this by the time elapsed, which is the 5 years, then we would get the average annual CO2 emission for that period from 2005 to 2010, which is displayed here. And we would just continue that process for all the other inventory years. Trying to improve each time the accuracy of the activity data or the classified lands. Each year comes with its own challenges, because when you're collecting Landsat images, we use different missions. So for example, for the more current years, like 2015 to 2020, we use our Landsat 8 image. Those tend to be crisp, have higher resolution, but as you go back, you use, like, for example, from 1995 to I think 2013, you'd have to use the Landsat 7 images, and they might not be as clear or have as higher resolution as these. Anyways, to continue, so you basically do that process for all the years in your time series, your inventory time series. So, all right, the future steps that we would like to take in improving the accuracy of our inventory is to conduct on-ground verification, and while using high resolution satellite image is acceptable and the most common way that verification is done, we would like to go out and actually do some assessment, so the underground really becomes the underground. We'd also like to reduce uncertainty in our maps by developing national or country-specific emission factors. As said before, the emission factors that we use were the default IPCC value. And so if we were able to get country-specific emission factors, so we develop emission factors for Jamaica, then that would better represent the local conditions that are occurring here. Would also love to be able to disaggregate the classes into more stratification, so as opposed to one class with forest, then we could disaggregate it to primary forest and secondary forest, and that will give us more accurate values in terms of emissions and removals. So those are some of the future steps that we would like to take. And I believe this is the end of my presentation. I would just like to thank you for your time. Thank you for attending. And I hope it was informative and that you have learned something from this today. All right.
Thank you very much, Tiffany, for that presentation. I certainly was kept very, very keenly fixed on the screen. It was very clear, and we certainly were able to follow the steps taken in terms of what you did. I am going to check. I have some questions of my own, but I'm going to ask if there's anybody who is online who has any questions or comments that they would like to share right now. You can indicate and I'll acknowledge you. I am not seeing any hands going. Oh, yes. Dr. Campbell, go ahead.
Hi, Tiffany. Thank you very much for an interesting presentation. I think you are a budding geographer, yeah? I just have a couple of questions. The first is related to, you know, the forestry department and whether or not, whether you're working directly with anyone there, because I see just based on some of the programs that they have upcoming, how some of this information would be useful to them. Yes, have you engaged the forestry department?
Okay, so the Jamaica team comprises of a person that is from the forestry department, but not necessarily that the forestry department is involved. So even with the example that I gave, that we use some of the land use maps to help us identify the land use areas on the map, she would have overlaid the maps, and I would have had some data also that I would have used to overlay, but there's no definitive MOU or any type of agreement where the information is freely shared. So I guess Dr. Campbell, I'll need to talk to you about that. But we're aware that they have been working on developing some of the emission factors, the country-specific emission factors for forest, which is one of the things that we are keen on. So in terms of a definitive MOU or agreement with them for this project, I'm not sure that there is, but we do have a member that is from the forestry department that is working with us.
Okay. Thank you. And finally, the forestry department produced a land use map from, I think it's a 2015 or 2014 ICONUS imagery. I'm wondering how different your results are from their classification. And I know that they also had one from 1998. I'm not sure if you.
That one is, I guess, accessible to the public. But like the more recent one, I think there are some sorts of agreements that doesn't allow them to share it openly with us. We'd have to look at those maps, but one of the things about the remote sensing is that the technology is always evolving. So for example, the Landsat images that we would have used for, so we went back all the way to 1990, even though that wasn't presented here, it's constantly improving, and so the newer images would be Landsat 8, and even the last session that we had, because it's a training session, it's continuous, we were told that there has been some improvement to the image, so we will have to rewrite all the codes that we have here now to reflect the Landsat 8 collection 2 image, and I believe the Landsat 9 mission will be launched. I'm not sure if it's next year. We'd have to rewrite the codes again to reflect those bands and those values. So it's constantly changing. with the expectation that it would be improved and the resolution and the accuracy will also be improved.
Okay, thank you. Because I think my two questions are somewhat linked, because it will be great for you to get access to that new, land use classification map that they have developed, because it looked pretty detailed, and maybe there's a way you can combine your techniques with what they've done to produce something much better. Yeah. So
Yes, definitely.
All right. Thank you.
Yes, thank you.
Hi, Tiffany. I have a question. So my background is in forest ecology, and that's where I started my postgrad research. You mentioned that you use like the Blue Mountains as a training area for the process, because that's forested, it's a protected area, we're a heritage site, it's not going to change, so that would be your reference.
Yeah.
But from an ecological perspective, if you think about forest types, like within the Blue and Jonker Mountains, you have, upper montane, lower montane, you have wet limestone forests. If you go to Cockpit Country, you have wet limestone, Hellshire Hills, which is another sort of constant area, Round Hill in Clarendon. Those areas are dry limestone.
Yeah.
In terms of your calculations, is it that all forests are going to perform the same, or you're just assuming similar performance from all forest types?
No, so all forests do not perform the same, and thank you for highlighting that, which is one of the steps that we had that I had indicated would be some of the things that we need to pay attention to. However, because we're using default IPCC values, it would be counterproductive for us to disaggregate the forest, to spend a lot of time to disaggregate the forest using different bands. So to start disaggregating by species type, then you have to start looking at infrared bands and playing around with that, as opposed to just using true image colors, your blues and your greens and your red, and seeing what you would see with your naked eye. To start using infrared bands and going through that process of disaggregating forests to what is limestone based species type. It would be counterproductive for us to do that if we don't have the emission factors to match that. So that when we get, okay, this is this amount of area of limestone forest, then this is the emission factor for that, and that is amount of carbon dioxide that is being emitted or removed based on this forest type. But that's definitely something that we are interested in, and that is a part of moving up in tiers in terms of the inventory, moving from our tier 1, which is just the basic preliminary step, to move into more of a tier 2 approach, where we get that granular detail of the type of forest that is there and how much is being emitted, now not only based on climate and region and land type, but based on ecology also. So we're stratifying more and getting more detailed and more accurate values.
Okay, so like a follow-on question, because I don't see any other hands up currently, is like, okay, so you mentioned like livestock and methane, and I thought that we have a few areas like Maynard and St. Anne and a few other large cattle farms and cattle areas. Would you be similarly looking to maybe pick up signatures from those areas in tier 2?
All right, so well, when we go to, so we have, I believe it's six different sectors, forestry and other land use sector. Then we have the agriculture sector, the energy sector. Each sector requires a different technique or methodology for the accounting of CO2 emissions. From my knowledge, when we begin looking at agriculture, the agriculture sector, then the values that you use to calculate emissions are, well, there's no removals here, but emissions, and usually it's the form of methane emission from enteric fermenters, enteric fermentation, which means these goats and cow passing off methane. The process that you use to collect data for that is usually from agricultural sensors. So we wouldn't use remote sensing, would have just used, because for this, one of the things that is said is that if you have the data already, you don't go through the process of the data collection. It's very expensive, it's very time consuming. And so what you usually do is use like consensus on livestock from probably Statin or from the agricultural ministry, and use the emission factors for those livestock to calculate emission on the agriculture sector. So you wouldn't necessarily use remote sensing data for animals. I'm sure it can be done, but it wouldn't be necessary.
Okay. All right. So it's a slightly, it's in another sector, which is the ag sector versus the forestry and other land use. That's the first thing. And then because you would more rely on the census rather than the remote sensing. Okay. All right. That clears up that for me. Is there anyone else who has any, it could be a comment or a question on any aspect of the presentation that they would like to pose at this time? Any other? I'm scrolling and checking. No. All right. Well, as I said, when I first took over after the presentation, it was a really clear presentation, very stepwise, and we could follow the transition in terms of the method and the calculations and how it was all done. So it is only for me to acknowledge persons like Joseph Prosper and calling you out all the way from Antigua, joining in, a former graduate of the department. So I'm recognizing each week the people who are were in the department and are joining us for these sessions. Very happy to have you. So it's really a pleasure to see the diversity of persons we have attending. And once again, to thank Ms. Wallace for a really engaging presentation, very topical. COP26 is underway, and so perfectly timed. David Lee says, excellent presentation, very important work, and that's in the comments. So I'm just the chat section, so I'm just reading it out. Some persons, because of maybe a connection or just being a little shy, maybe not going to speak up, but it's in the chat. Excellent presentation, very important work, and it is important work, and I'm glad that we are a part of this Caribbean hub and that you're contributing to the region and to Jamaica's research agenda. So thanks for sharing with us.
Yes, thank you for having me.
You're most welcome, very welcome. And for those joining in, every Thursday, 1 o'clock during the semester, this is where we are. You're welcome to join us each week for varied but engaging topics from either geology or geography. So I look forward to seeing as many of you as possible next week or in the weeks ahead. So thank you for joining.